All right. So getting started today. Um, a lot of times when I do the PowerPoint notes after I've annotated them, I will make a PDF version and I'll put it in the daily assignment and all of that, and I'll do that. Every day, it may not always be this class period, but since this is my smallest class period, this is probably the one that I'll record in. So like if you see this on me, that just means that I'm recording the lesson. I always post the video. So if you ever miss a day, make sure you check Google Classroom that day, but wait towards the end of the day because I don't usually post it until the end. Sometimes I'll go back and edit a few things in the video, or shorten it a little bit if I have an intro today, so I'll probably shorten that and cut that off, things like that. All right, so our outcomes for this chapter, for chapter 1. It's the main goals for today. We need to be able to define the term chemistry and identify substances as chemicals. Know the definitions of chemistry and matter. Describe activities that are part of the scientific method. Know definitions of hypothesis, observation, theory, and law. And then be able to differentiate between observations from theories and from laws. So some real simple basic definitions. A law is an observable relationship between two values. I'm going to give you a couple of different ways to say that same thing today. A theory is an explanation to explain why the relationship exists. And a hypothesis is an explanation that is not yet supported by a lot of evidence. So the hypothesis, think instantaneous, versus theory, think something that's been going on a long time. All right. Now, that's just kind of our goals for today. All right. No, I forgot to do something, so I'm trying to do it before we get there. Now, that's something else that I want you to know. Not everything. A lot of times on the things that I want you to write from the slideshow, I will underline or highlight as I go through it. Again, I'll post most of my notes. Most of the time, anything we go through, I'll post them at the end of the day as well, just so that we can that you can have access to that. But I do want you to get, especially anything that like I handwrite on the screen, that's the things that I really want you to know, that I'm just kind of adding to some stuff. All right, so that's where I'm going to stop. All right, and hopefully that works. All right. So one of the main thing that we're going to start with is separating the idea of what is considered to be matter. All right. So starting off with this, anything that you can touch, feel, interact with using the senses is, well, sorry, anything that you can touch or feel is considered to be matter. There are some things that we can't technically touch that are still considered matter. Some of them is just because they're too small for us to realize we're interacting with them. But for the most part, anything that you touch or feel is going to be considered matter. So all things are made of, everything that we can touch or feel is made of either atoms, molecules, or some mixture thereof. All right. So the most important idea of all human knowledge is all things are made of atoms. All right, that is Dalton's first statement. That is the kind of the primary thing, and that's something we've been realizing since ancient Greek philosophers and things like that. The word atom actually comes from a Greek word that means uncuttable. That there's a point that you can keep cutting something till you get to a point that it's uncuttable. Now, we know that we can split an atom at this point, but back then they couldn't get beyond that point. If they did, we probably wouldn't exist today. All right. So first idea about an atom. Remember, atoms are very small. We cannot see an individual atom. You can see multiples of atoms. I think the best image that we can get with the best electron microscopes or scanning electron microscopes, I think, is about 10,000 atoms at one point. I think that's the best image. And those are going to be very large atoms that we're looking at. So just remember, they're not going to be super visible. Atoms and molecules are tiny particles that compose all matter. So in order to be considered matter, it has to contain atoms. Now, before I move off of this one, so give me an example of something in this classroom that would be matter. The wall, all right? What about, is there anything that we can't necessarily see in this classroom that's still considered matter? The air, the oxygen, the nitrogen that makes up the air, all right? So that is matter. What would be an example of something in this room that is not matter, but we can still see it? Light. Energy is, so it's either going to be matter or energy. All right. So if it's not matter, if it's not composed of atoms, then it's going to be energy. So energy is things like sound. Well, sound waves manipulate matter so that we hear it. But the energy that produces the sound wave is the energy side of it. But light, heat, to some degree, electricity kind of hits that fine line between matter and energy, because electricity is the movement of electrons or movement of certain particles, but there are non-matter components of it. It's not a full atom that's causing that electrical current. It's just the electrons. All right. So atoms are bound together in several different forms, in several different types. They're called molecules. So when you have two or more atoms combined in a certain way, you get what's called a molecule. So this should be a familiar molecule to you. What molecule would that represent? Water. All right, so that's H2O. Another one that you may not realize right off the top of your head, carbon dioxide. All right, those are just basic ones. You've seen them, you've interacted with them. I can get more complicated. That's glucose. All right. You don't need to know that one today. All right, I'm just kind of going through there. All right. So when chemicals form molecules, they are attached by chemical bonds. That's what holds them together. You can have just two atoms interacting with each other that are not chemically connected. So, for example, in our atmosphere, we have nitrogen gas, we have oxygen gas, we have water vapor, we have carbon dioxide, we have carbon monoxide, we have helium, all of that in very, very small parts. The majority of the air that's in this classroom right now is nitrogen and oxygen. Nitrogen represents about 70% of it. Oxygen represents about the other 28%. Or another 28%. The remaining 2% is between all of the minor gases like water vapor, carbon dioxide, helium, hydrogen, all of those things that are just kind of floating around. All right. So, basic definition of chemistry. Chemistry is a science that tries to understand how matter behaves. Is the simplest I can give you. All right. So our goal in here is to kind of look at and discover why some elements react with other elements, why some elements don't react at all, why we have to be careful. Why we have to be careful with certain things around fire. Why some things just don't never catch on fire. Why are some things able to quench a fire? Things like that. So let me see if that's where I want. All right. Yeah. Okay. So, all right. I'm gonna skip that. Skip that. All right. There's not anything on this next slide to copy. I'm just going to bring this up. All right. So, chemicals compose ordinary things that we deal with. So, some ordinary things that are composed by chemicals: the air we breathe, the water we drink, things that we interact with: toothpaste, Tylenol, toilet paper. I don't know if it was this class period or whatever. They were asking me some things, and like there's chemicals that I have in that closet that I can take it from the chemical that it is right now to converting it into what we would call aspirin, acetylsalicylic acid, and then I can take that acetylsalicylic acid and convert it into acetaminophen, which is Tylenol. All right, I've done those labs in my undergraduate studies. Now, do I make a regular habit of taking the stuff in there and doing that? No, because it's cheaper for me to just go to the store and buy the Tylenol that I know is done correctly versus me trying to make, and what I would make would be more like if you ever seen the BC powder, it's going to be in powder form, not in capsule form or things like that. All right. So, daily things that we use is all considered matter. Now, so when we're looking at matter, why is water a liquid? Why do you think water is a liquid most of the time? All right, so something to do with atoms. I heard something here. Okay, they're farther apart. So water is kind of a funny substance. That's why we compare just about everything else to it. So water, as we showed before, what are the atoms involved in water? H2O, 2 hydrogens and 1 oxygen. All right. So now we don't know that water actually looks like this, but that's how we kind of draw it. Sometimes you'll see it drawn more like a Mickey Mouse, upside down Mickey Mouse head, like that, and all of that. What we do know about water is that it has an end of it that tends to be more negative and an end that tends to be more positive. And so we associate the hydrogen side as being the more positive, the oxygen side being more negative. All right. What that means is there's a certain attraction between this end and that end. So if I had another water molecule here, it's going to line up to where the oxygen side's pointing that way, and there's a little bit of attractive force between them. So water has enough stickiness between the molecules that it keeps it close together, but not so far apart that it's a gas, and not so tight that it's a solid. That also is why water's unique in that its least dense state, or sorry, the solid state is actually less dense than the liquid state. Most things, the solid state is more dense than it. Gas is still the least dense state. All right. So water being a liquid has to do with the elements that are involved and the arrangement of the elements in the molecules. Same thing with why is salt a solid? It has to do with the elements that are involved. Those sodium and chlorines make positive and negatives, and it makes a crystalline structure. Why does something like Coke fizz when you open it? The carbonation. What is the carbonation? CO2. All right. Why is the sunset red versus when the sun is higher in the sky and it's kind of a yellow? And it has to do with the light, the energy passing through different parts of the atmosphere. So we're seeing a thicker part of the atmosphere when we look at it on the horizon versus when we look at it straight up. So it's more refraction. All right. So scientific method. And you're going to hear it called different things. I've been teaching for a long time, so I still say scientific method. Engineering process, scientific method is all the same thing, just a little bit different verbiage between one and the other. But scientific method is a way of learning that emphasizes. Sorry. Yes. I haven't posted them yet. Once we get access to Moodle, it's the chapter 1, and I'll show y'all how to get there tomorrow when everybody's in. Scientific method is a way of learning that emphasizes observation and experimentation. So you see something, you have something you know you want to accomplish, you do trials over and over again until you get to where you want. One of the things that kind of separates scientific method from engineering process, usually with engineering process, you have an end goal in mind. There's something you want to accomplish. You want it to function a certain way. Whereas scientific method enters in with, you may have a preconceived idea, but that doesn't mean your end result is going to end up with what you thought it was supposed to be. All right, you think it's supposed to work this, you think it's supposed to do this, and then it actually turns out to be something else. But no matter what, we're going to try to produce knowledge as a result of the senses, the stuff that we can physically interact with. So, like this morning, how many of y'all drive? All right, this morning when you went out to the car, could you see out your windshield when you first got in there? Why is that? Ice. It's cold out. So why does ice get on your windshield? The water vapor in the air. So if it's cold enough, the ice condenses, and then if it's really cold enough, the ice can make crystals and all of that. So the glass on your car might be able to get a little colder than other parts of your car. And that's why it only appears on the windows or things like that. So we can use those observations and we can do tests to figure that out. I'm not going to go into, we're not going to go into the test, but we can do things to try to figure out why that happens. All right. So, all right. If you want to draw this, if you want to take a picture of it, either way is fine. But this is kind of how scientific method works. Your starting point is typically going to be some sort of observation. All right. From there, after we make some observations, what's kind of the next area that we have to go into before we can decide if we're going to make a hypothesis to test or if it's already something that's been tested? What's an area that we have to do? Research. All right. So somewhere after you make your observations, there has to be some research that's done. And then in your research, you may find out that there's somebody that talks all about this. I'm sure there are tons of information of why water condenses at night or in the mornings and all of that. All right, so I know that there's probably either some kind of law or some kind of theory that's already associated with that. It's probably called the water cycle, that kind of thing. All right. Now, if I find that my observation doesn't have anything on it, nobody's researched it yet, and all of that, I start making an idea, that hypothesis. Now, in the past, when you talked about hypothesis, how did your teachers have you write hypothesis? I think because statements, you might, if anybody in here like computer science people, programming people, when you're trying to get a computer to compare different variables, how do you write that statement usually in programming? If then. So I think because if this happens, then this will happen. I think this happens because this happens. Both of those are testable statements. So the big thing about a hypothesis, it has to be a testable statement. So we go in, we test it. Maybe our first statement, we didn't have a clear enough statement to test well. So we go through there and we find out that what we were trying to test was totally irrelevant to the result. I could say something like, I think students that are born in October are going to make better grades than everybody else. And I can test that. And then when I test it, I'm going to find out there's nothing true about that statement at all. So I might have to refine that. And then I'll say maybe left-handed students are going to make better grades than right-handed students. And I'll test that, and I'll probably find out that there's no validation to that. But I can keep going through there and all that. That's why I don't like psychology, because that's what psychology tests, those kind of things. It's just very random things about people and animals that you can't really control. But the thing is we will keep going into experimentation until we either totally prove or totally disprove a hypothesis. If you test a hypothesis and it works 8 out of 10 times, I still wouldn't be able to say that hypothesis is necessarily true. I need to figure out what happened on those other 2 times. Was it a human error or was it something that is legit messed up? All right, from there, if it's a law, there's really no need to test it anymore. Do we really need to test on Earth? Do we really need to test that an object falls at 9 or accelerates when it's falling at 9.8 meters per second squared? No, it's going to happen that way over and over and over again. Do we need to test our ideas on what we think the shape of atoms are or the shape of molecules are? Yeah, we still need to get there. So that's ongoing. That's going to be So that part, atom shape, atomic theory, is a theory, not a law, whereas gravity is a law. We understand gravity enough that we don't have to explain it every time. Now, just so that you know, anybody in here like a Doctor Who fan? Watched any of the new shows? Maybe it's just an old people thing. All right. So anyway, Isaac Newton is the person associated with gravity. What's the idea of how he discovered gravity? All right, sat on a tree, an apple fell on his head, all of that. Actually, if you look up what Isaac Newton did, he wrote something like a 935-page thesis and mathematical proofs of gravity on Earth versus gravity of other planets and all of that. So it wasn't just that he saw an apple fall. There were a lot of tests associated, and it has a lot to do with mass and relative distance and things like that. So there's different parts of the law of gravity. On Earth, objects always fall at the same rate, or accelerate at the same rate as they're falling. Between Earth and Jupiter, there's a certain amount of gravity due to the mass of each planet. There's a certain amount of gravity between Earth and the Sun because of the different masses and all of that. He also wrote the universal gravitation law as well. We can calculate those numbers. So anyway, going from hypothesis. After you've tested your hypothesis enough, it may end up being a theory. You may have to revise that hypothesis, though. All right? So as a theory, that means that it's been tested or confirmed over a long period of time. So things like atomic theory, things like, trying to think of another one that's germ theory, which is kind of like it's leading into medicine and, you know, why bacteria and viruses act a certain way and all of that. Those things, we have multiple tests to see how they respond. We know that when a virus is introduced to a system, that it's going to have an exponential growth curve. That, you know, one person gets it, then usually 2 or 3 more gets it, and then beyond that, those people all get it to 2 or 3 people and all of that. And so you see this really large growth curve for it. And then it reaches a certain point on its apex, and then it's going to come back down. And it won't usually come back down to the slow curve. It usually spikes down, like it almost just drops off, because there's a certain point that immunity hits. All right. So theory, the great thing about theory is every theory that's out there has a lot of hard evidence for it. But because it's a theory, when we find something new out, we can still modify it to make the statement more correct. And then from there, with the theory, you do some more testing. Eventually, if it's tested enough and it's always proven to be true, then it can go back to a law. So the thing about scientific method is a cycle. You keep testing it until you see that it doesn't need to be tested anymore. And it doesn't necessarily just mean that one person is testing it. People all over the world need to be able to test it and get the same results. All right. I will say this. So like for Newton has 3 laws of motion. He also has gravity, things like that. It was a lot easier to get something called a law back then than it is now. Just because we have more resources and tools to test things and maybe find those anomalies. Like when we start looking at internal motion of an atom, Newton's laws of motion break down. So parts of physics are starting to disprove the 3 laws of motion inside of an atom. Not macro scale, it always works, but micro scale, it doesn't. So that's just some things. All right, so here's some basic definitions. So observation. An observation involves measuring or observing some aspect of nature. So how do we observe things? Our eyes, hearing it, touching it. some way of manipulating it without changing it, right? So an observation is always going to be some sort of interaction with something that we don't change what's happening. So, like I can observe that the water in my cup is a liquid. I can observe that my breakfast, the syrup that I put on my waffle this morning, flows more slowly than water. I can observe those things, and I don't really need to change what they are. And then I can do tests as to why. All right. So a hypothesis is a tentative interpretation of an observation. So we see something, we observe something, and then we make a tentative explanation or interpretation of it, that I think this happens because, or if I do this to something, this will happen. So the thing about a hypothesis, that's is almost like an opinion that we make in our head on something. Doesn't have to be correct. We don't even have to have, other than just some qualitative observations, we don't have to know anything about it other than just some basic research that we've done and some things that we've seen. So it's not yet supported by evidence. All right. For a law, because a law has been proven true time and time again, most of the time when we interact with a law, it's going to be a summary. So, I can say, and I can make that statement, and we know that as a law. I can make this statement, and does anybody recognize that second statement? Force equals mass times acceleration. What law is that? Newton's second law. All right. And then equal and opposite reactions. It's Newton's third law. Things, I can say an object stays in motion, and y'all can probably finish the statement. An object that's in motion stays in motion. An object at rest tends to stay at rest. That's Newton's first law. All right. So those things, we don't really have to explain why we know that. We just know it. All right. Now, so laws tend to summarize the results of a large number of observations. This statement, I've had this in the outcomes. The reason why I put these two statements here is I have found in the past that Southeastern likes to use those statements in a test. All right, and stated that way. So, an observable relationship between two values is another way to look at a law. And then a theory. Theory is a model that explains and gives underlying causes for observations and laws. So a theory tries to explain why the relationship exists. Big thing about theories, theories have lots and lots of data that can support it. Make sure I'm staying on track of what I wanted to do. All right. So, freeze that right there. All right. So, not really anything that you need to write off of this one, but I want to talk about Lavoisier just for a minute, and then I'm gonna do a demo. All right. Now, some statements about a hypothesis. We've already talked about the definition of a hypothesis. The thing that makes a hypothesis work. So if you're looking at a list of statements and trying to determine which one of these is a hypothesis, the thing that makes a hypothesis good is the ability to be falsifiable or the ability to be provable. All right. So a good hypothesis is falsifiable, which means that further testing has the potential to prove it wrong. Because that's the whole thing, is you're trying to make a statement that you can, without a shadow of doubt, either prove correct or incorrect, true or false. And then the way that we do that is through experimentation. So I would know a good hypothesis is falsifiable, and it's tested through an experimentation. Anybody need more time on that one?
Yeah.
Okay. Again, don't feel like you have to write every word that's up there. All right. So I'm going to move on again to theories. Remember that a theory is kind of like an expanded hypothesis, one that's been tested over for a long period of time. So we're going to look at that. So a hypothesis tends to be very specific to one thing, something you can test immediately. Whereas a theory is going to tend to be a broader statement covering more area. So if I can get it to go. So if you have several hypotheses that apply to one area of study, then we can start forming a theory if they all kind of lead in one direction. So remember that a theory is a broader, deeper explanation of observations and laws. It's just a way it's just kind of a way to predict future things. So I'm going to pull those up. And I'm going to point this out. A lot of times, theories, this word model is going to appear a lot with theories. All right. Because with theories, we can create models and simulations of what we predict are going to be the future. So climate theory, that's one that you may not have ever heard climate theory, but you've been exposed to it almost every day of your life through news media and through political pandering. All right. Because we've had a lot of data on weather for years and years and years and years and years and years, we can attempt to predict future weather patterns. We can also predict future things about global temperature and all of that. Not getting into the political side of it, there are all kind of models and simulations that predict what will happen if this much carbon dioxide or this much water vapor or this much methane gets in the atmosphere. And when it's typically reported to the masses, they pick one area of the data that they want to focus on. And it's usually the opposite extremes of the modeling thing that came out. So one side's going to pick this one and say, oh, in 10 years, everything's going to be gone. Oh, we've got 10,000 years before it happens. Whereas the reality and what the scientists actually look at is, where does the data centralize? All right. And so when you're doing that and when you hear those things, remember that consider the source of where you're hearing it. If you have a legit scientist standing up there, which you're probably not going to want to listen to, but when you're in college, some of the courses you take, you'll get extra credit for going and sitting to them. So you will listen to them on those. But whenever they're going in there and talking, it's going to be very boring, and it's going to be just tons and tons and tons of data. And they'll say, we ran the simulation with these factors, and this is what happened. We ran the simulation with these, and this is what happened. And then they'll usually come down and say, the consensus is this. So theories are kind of used to predict behavior that we kind of see. So we're going to spend a lot of time with atomic theory in this class. And what we've discovered over time is that atoms and molecules act in predictable ways. And so we can use what we understand to be of the way things happen and predict what's going to happen in the future. We can predict if an atom has a certain number of electrons in its outer shell, it's going to react with certain other atoms. We don't have to know exactly what it looks like. We just have to know that this is how it reacts. And that's kind of the big deal. And then only one other statement that I'm going to focus on from theories is really this one. If we start finding things, our hypotheses and all of that are trying to support a theory, as we gain more information, poor theories are eliminated and good theories are replacing it. All right. So atomic theory, which this class is kind of based around, if we go back our first idea of atoms was just that it was a solid sphere, that we could cut stuff down. Really, it wasn't even necessarily a sphere. It was just a solid hunk of mass that could take on a shape that fit what they thought that substance did. All right. But it was just like so you could think of like maybe a pool ball or something like that. But then a little bit later, we discovered that atoms aren't solid. Or we discovered that within that solid mass, we had different things, so different areas that were either positive or those little circles are negatively charged. And then we discovered a little bit more that atoms have this dense solid center, and then there's things on the outside. And now we're to the point that we still know that there are protons and neutrons in the center, and then we try to say that an electron may be there, that electrons exist in fixed areas, and we have to mathematically prove where they might be. All right. Our understanding of the atom has changed over time. We don't think of the atom the same way that we did in the 1800s. Now, we've changed that. So as we get more information, we make better things or make better ideas. All right. Let me make sure that's as far as I wanted to go. Yeah. All right. So that's where I'm going to stop it today.